The scope of this includes material extraction, processing, and transportation. So it's basically from extraction to the gate of the mixing plant. This includes mixture design and proportioning, as well as mixing plant operations. And the process that's, or the framework in which these things are discussed in the reference document is within a life cycle perspective. As Tom mentioned, for aggregates, similar for asphalt binders, it's a big deal economically in the United States. There are currently about 46 refineries in the U.S. producing asphalt. We used about 130 million barrels in 2011, which is down quite a bit since the building boom in the middle of the last decade. That was worth about $7.7 billion. 83% of the asphalt binder used in the U.S. goes for paving purposes. Most of the rest goes into roofing, and a little bit goes into insulation in cars and pipelines and such. More than 92% of all the paved roads in the U.S. are surfaced with asphalt mixtures. And on the asphalt mixture side, the U.S. has about 4,000 plants producing asphalt mixtures, about 400 million tons in 2010, and the value of those mixtures in 2007 was about $11.5 billion. So this is a big and widespread industry in the U.S. Some of the key issues for asphalt and asphalt mixtures are the price of petroleum and asphalt, which is clearly a finite resource. Prices have been somewhat volatile in the last decade. The environmental, social, and cost implications of mixture design and durability, basically getting the maximum benefit socially from our asphalt materials while trying to minimize the cost and the environmental impacts. Appropriate use of polymer, rubber, and other types of binder modifiers. Depletion of easily accessible high-quality aggregates needed for some types of mixtures, which Tom was talking about. Specialization in mixtures, the right material in the right place in the pavement at the right time for safety, noise, and structural considerations, and then balancing those with the environmental and cost implications. Rapidly increasing use of recycled asphalt pavement and other recycled and waste materials, including recycled tire rubber, asphalt shingles, and sulfur, and future binder availability and alternatives. So asphalt is produced in many different forms for use in pavement. The most typical, and we have a picture on the left there of an asphalt cement, which is refined from oil. We can take that same asphalt material and suspend it in water to help us be able to spread it and use it in various applications, which is called an emulsion. We can create what we sometimes refer to as asphalt champagne by foaming asphalt in water, and not used very much anymore, primarily for environmental reasons. We can also make asphalt liquid and spreadable by mixing it with a solvent. On the right-hand side there, you see an example of an asphalt rubber mix where recycled tire rubber has been digested into the asphalt cement. Asphalt comes from crude oil. So the life cycle from extraction to the gate of the refinery starts with the oil well, bringing it forward to the refinery, various processes in the refinery, which then result in breaking that petroleum source into various products, from gasoline at the upper light end, or gas actually, at the upper light end, and asphalt, which is the heavier molecules in the barrel of oil, which are used to produce asphalt cements. And then we may take, as we just talked about, that asphalt cement and process it into emulsified asphalts, or use it in various types of, with modifiers to modify the asphalt. This is apologize, the source is not put on this. This is from a study by Rebecca Yang at the University of Illinois. What's shown here is some of the different sources of greenhouse gas emissions from asphalt production. And the PADD shown here are petroleum-producing districts in the United States. So this is just giving us a little bit of an idea about what are some of the main sources, in this case, for greenhouse gases as an impact indicator. We can see that most of the impact for this impact category comes from extraction and refining, very energy-intensive processes. And that we can see that regionally the main sources of variability have to do with the different sources of oil being used in these different regions, the flaring, the refining processes, and as with aggregate, as with all pavement products, materials, the amount of transportation that's involved in getting it to the location of use. The asphalt materials and mixtures, the main product that's used is in hot and warm mix asphalt. These are the primary structural materials we use for pavements. There's a variety of dense and gap-graded mixtures. Each one can be designed for a specific function in the pavement. On the wearing surface, we're looking for friction, for skid resistance, and rutting resistance. Those pavement layers, asphalt layers, also spread the stresses from the load and protect the unbound layers in the subgrade down below. So we're looking at the stiffness and thickness of those intermediate layers. Layers at the very top and at the very bottom, we're particularly interested in fatigue and fracture resistance under repeated traffic loadings. And asphalt mixtures are also used extensively as base materials for concrete pavement. Another kind of hot and warm mix that we use is open graded mixes, and those are used as thin wearing surfaces, and those provide even more friction and take the water off the surface of the pavement, which reduces the risk of hydroplaning. And because they're on the surface, we need them to also resist rutting. What is a dense graded asphalt concrete made of? And this is actually the same slide that Tom showed, emphasizing that it's 80 to 85% aggregate by mass. But we can also see that there's 10 to 12% asphalt binder in there. There's 2 to 3% dust and air voids. The trends in asphalt, dense graded asphalt mix design include specializing these mixtures for the specific purposes in the pavement that I just went over in the previous slide. As part of that specialization, using polymers and crumb rubber in particular places in the pavement where they can enhance performance, greatly increase use of recycled asphalt pavement to replace some of that 10 to 12% of the asphalt binder that would otherwise be virgin asphalt binder coming from the refinery. There's experimentation with the use of recycled asphalt shingles also for binder replacement, and then a slowly increasing trend for the use of kind of high-tech performance-related testing to check those specific properties that we're looking for in the mixtures for each of the different locations that we're using them in the pavement. The basic process of dense graded mixture design is to identify what's the function of that mix in the pavement layer. And kind of the point of this slide is to emphasize to the folks out there that a one-size-fits-all for mix design specifications is probably not the most efficient from a cost and an environmental point of view. If you have different uses in the pavement structure for different mixes, your criteria for the mix design are going to change. So the basic process is to identify that function in the pavement layer. The next step is to identify the appropriate asphalt binder type or grade, which in the PG system, which we use across most of the country, is based on the temperatures, the stresses and strains, and the traffic repetitions that mix will be subjected to. And the stresses and strains and temperatures vary on the depth within the pavement, if it's a wearing course or a structural course. And then the decision about whether to use a conventional asphalt binder or polymer modify it or rubberize it to enhance the properties for specific purposes. We need to identify and test the aggregate sources and gradations, and then based on volumetrics, select the final binder content. Now, where the project importance warrants the extra cost and particularly the extra time for performance-related testing, we can specify specific properties that are checked with laboratory testing for stability and durability performance to further try and optimize that mix for the specific purpose. And mix design should always include consideration of recycled asphalt pavement. Some other uses of asphalt materials and mixtures, more and more existing pavement layers are recycled in place through partial depth recycling and through full depth reclamation. Partial depth recycling is recycling 2 to 4 inches typically of the pavement surface. Full depth reclamation is recycling the all of the asphalt layers in place. And we can see on the upper right a full depth recycling train. Asphalt is also used extensively for maintenance and preservation seal coats such as chip seals, microsurfacing, slurry seals, and fog seals. Apologize to everyone, we're losing the bottom of a few of our slides here. The last item there is that we also use asphalt in tack coats and prime coats, which are very important in multi-layer asphalt pavement tack coats in gluing the different asphalt layers together to achieve the maximum performance from the overall pavement structure. What is RAP, recycled asphalt pavement? RAP is milled or pulverized existing asphalt materials, and we use those in a variety of purposes. For a variety of purposes, what we call the highest use, and we'll talk about that in just a minute, but the highest use is to recycle these back into new asphalt mixes, which can be done either at the plant or in place. Plant recycling, it produces higher quality, more consistency. In place recycling reduces the transportation impact. So two things to consider on whether to recycle at the plant, haul it to the plant and recycle it, or recycle it in place. When RAP is used in new asphalt materials, and these are approximations of percentages here, different agencies will have different specifications, but you can easily use up to about 15% with no special considerations in the mix design, and up to 40% with some special consideration in the mix design, which can offset a great deal of virgin aggregate and asphalt binder in the mix. Partial depth recycling, you're mixing with hot or cold asphalt, and full depth reclamation, you're mixing with small amounts of asphalt or cement or other stabilizers. The lower uses of recycled asphalt pavement would be things like aggregate base, shoulder backing, etc., but which are not taking full advantage of the asphalt binder that's in the RAP. What are warm mix, crumb rubber, and polymer? Warm mix is a variety of technologies, a wide variety of technologies that can help us reduce the temperature needed for mixing and compacting asphalt mixes. This has 2 advantages. In my mind, the first advantage is this can really help us get better densities, get better compaction, and increase the durability of our asphalt mixes. Warm mix technologies can also potentially help us reduce the energy needed for mixing in the asphalt plant by reducing the temperatures we need to mix at. Polymers are used for various, polymers come from petroleum typically, although there are some other sources, and these are used to change asphalt properties, improve asphalt properties at different temperatures. They carry their own environmental impact. but if the performance benefit and the environmental benefit of improving performance is greater than the environmental impact of producing the polymer, we get a net benefit. Crumb rubber modifier comes from ground recycled tire rubber with the steel removed. It's chopped up. There's various sizes that you can use. It acts as a polymer. It can be mixed with asphalt, cement, natural rubber, and other ingredients to create rubberized asphalt. It can also be used with polymers in rubber-modified binder. And there are various other, there's a lot of work going on right now on various uses of crumb rubber modifier. There's a lot of tires out there. In California, we each are responsible for about 1.5 tires a year that would otherwise go into a landfill. Again, as Tom was talking about, the trade-off of recycling it, the benefit in performance, needs to be compared to the benefits of transportation, the impacts of transportation and processing. In general, though, the net impact will be positive. Looking at just, again, global warming potential is one environmental impact indicator. There are a variety of others. But looking at this one impact indicator, in a given project, this is all of the an analysis for an example project, and each project will be different, of where is the impact in terms of global warming potential in the asphalt used for this project. We can see that most of the impact is in the plant operation, and this is a place where warm mix asphalt can potentially be used to reduce the plant operation energy. We can see that the next biggest source of impact for this example is binder production, production of the asphalt. And this is a place where wrap can be used to reduce the virgin binder content. We can see that the next biggest category is aggregate production. And again, wrap can help us reduce the amount of virgin aggregate that we're using. We may have a slight increase in plant operation energy from using the wrap, but in general, we're going to get a net benefit from that. As Tom talked about, the use of the wrap, one of the things to consider is, am I having to haul that wrap from a long distance away using trucks? So these are some of the considerations, but in general, overall, for most examples, using the wrap is going to help us with a number of these different categories, and using the of impact and the warm mix is going to do the same. This is pretty clearly recognized out there, and we can see that most of the wrap that's produced out in the United States a few years back, and I believe the trends are probably growing, continuing to grow. Most of the wrap is used in new hot mix and warm mix mixes. Much smaller amount is used for next higher use as aggregate. Some of it's used in recycling in cold mix, and very, very little is landfilled, as we can see here, a tiny amount. Wrap has value. It has value as aggregate and asphalt, and that's clearly recognized in the industry. And the more that we can facilitate this and still get the kind of performance and durability that we're looking for, we can continue to reduce environmental impact and cost. We can also see that warm mix is growing by DOTs, by local agencies, and the private sector, growing rapidly. Helps us get the density and can potentially help us reduce the energy in plant operations. I mentioned highest use, and this is discussed in the reference document. The highest use is where does it offset the environmental impact the most. This depends on the project, what is technically feasible, evaluation of the net life cycle environmental impacts, and prioritization impacts. We've shown a couple graphs of global warming potential, but there are a number of other impacts that should be considered, such as air pollution, water pollution. In the arid west this year, water use, a number of environmental impacts that should be considered. Is recycling always the best strategy? In general, it is. But one should always be aware, a couple examples, if you have a locally available material, virgin aggregate, and your wrap is a long ways away, you're going to want to consider that